But before we go to the actual hands-on session, let me motivate you, or let me continue from where we left off yesterday, which was at the point of introducing the Einstein Toolkit. So this we briefly covered yesterday. So these are the steps that one needs to ensure that are being held even before one wants to do numerical simulations on the computer. So again, we need to make sure that we are writing Einstein's equations as well, pose the initial boundary value problem, discretize the resulting PDEs, specify boundary conditions, find a way to deal with singularities, choose our favorite gauge conditions, and so on. Then, assuming you have all of that, and typically during a numerical evolutions, there's still a bunch of things that you need to account for. In particular, you need to be able to solve for the initial data that you want to be evolving. And this by itself is a task that is non-trivial. Then, in order for you to be able to do the evolutions on your machine, you need an efficient mesh refinement library that allows you to efficiently handle the different length scales that you have in your problem and parallelize the resulting algorithms. And of course, you want to be able to do this in the most efficient way possible. And this is precisely where Cactus or the Einstein Toolkit enters the problem, right? So for a typical problem, not just in numerical relativity, I mean, many of these things are transversal to many fields of computational physics, such as fluid dynamics, for instance. But in particular, for numerical relativity, for a typical problem, you need to have, you need to have this list of things, right? So you need to have some mesh refinement library. You need to have an infrastructure that efficiently parallelizes. You need to be able to handle usually very large input and output. And then you need, of course, somewhat complex tools for analysis to extract whatever physical quantities you want to study. And so if you notice, I keep losing my mouse, but I think it's, yeah, here it is. So each of these, so in particular, these three items here, this is not physics. It has nothing to do with physics, right? These are problems of, at best, high-performance computing or algorithmic problems. So typically, this is not the thing where you want to be spending your time, right? So typically, you have a problem when you want to extract physics. You don't want to be implementing. You don't want to be studying. Is already providing this for you, so that you don't have to worry about that, and so you are able to just worry about the physics. And this is what this library, the Cactus, provides. The typical workflow is that you need, this is quite transversal for time evolution problems. The way it works is that you need something that computes the initial data for you, then you do your time evolutions, and at the same time that you do the time evolutions, or sometimes at post-processing stage, you do your analysis. Now, I've been talking about Cactus and the Einstein Toolkit. So what is, let me now try and define this thing. So what is Cactus? Well, Cactus is a tool, it's a general framework for the development of portable modular applications. It's relatively old now. I mean, the very first version was, I think, was released around, in the 90s, so around 96, 97, something like that. And it has grown somewhat organically since then. The whole idea behind Cactus is that the programs are split into these independent components that are called the thorns. So, and ideally, each of these thorns should be, or would be able to be developed independently, and should be interchangeable with others with the same functionality. So this is why this tool is called the Cactus, right? So you have the Cactus flesh, and you have the thorns of the cactus. So thorns don't directly interact with each other; they interact via the Cactus framework, the flesh, which sort of provides the glue between each of these independent modules. Okay. An advantage also of this framework is that it supports applications in C, C++, and Fortran. So people don't need to be arguing about which is your favorite programming language. Some people prefer C, some people prefer C++, other people prefer Fortran. So everyone is happy. Everyone can just pick their own favorite language as long as it's C, C++, and Fortran, which is already not bad. Okay, so what is then the Einstein Toolkit? So roughly defined, the Einstein Toolkit is essentially Cactus, so this infrastructure that I was just mentioning, plus a collection of thorns, so a collection of modules that are specific tools for numerical relativity. So Cactus by itself does not know anything about Einstein's equation and doesn't care about Einstein's equation. So in principle, you're fine you're fine to use Cactus for any sort of time evolution problem. If you have computational fluid dynamics, if you want to be modeling the stock market, you can use Cactus in principle for that, for anything that you can model as a time evolution problem, especially if it's something that relies on a three-dimensional grid. Cactus is a good tool. The Einstein Toolkit is this framework that takes all of that infrastructure and adds specific specific tools, so specific thorns in the language, in this language, and those are specific for numerical relativity, such as routines to compute different sorts of initial data that you may be wanting to evolve. It provides a solver for the vacuum Einstein equation, so something that evolves the vacuum Einstein equations. It also provides solvers for the hydrodynamics equation and for the coupled system. And it also provides a lot of very handy analysis tools, such as tools to compute apparent horizons and to compute wave extractions, and many more. So this is a very rough history of the toolkit. So again, so Cactus dates back from the 90s, but so the Einstein Toolkit itself, the first version was released in 2010. There's a vibrant community that develops and maintains the code base and different thorns that are used, and typically people try to have a new release roughly every 6 months or so. So the current version was released last December. So there have been many contributors over the past decade from all over the world. So the goals are roughly this year. I think I took this directly from the website. So it's a community-driven software platform of core computational tools to advance and support research in relativistic astrophysics and gravitational physics. So, and the idea behind this is the same as Cactus, in the sense that you want to separate physics from computational science. This is what I was telling you before. So you don't want to be spending your time figuring out what's the most efficient way of performing input and output, figuring out the most efficient way of parallelize your code, right? Those are very interesting. Those are very interesting problems, but those belong in computational science. So if you want to be doing physics, then we have our own problems to think about and to be spending our time. Yeah. So the idea is that the Einstein Toolkit is providing this in a way which is well maintained, of high quality, sufficiently easy to use, and also very importantly, that is open source. Okay. So this is open source, open development, so it's free for anyone to just download and start using. And how do you do that? Well, you just go here. Let's see if the internet is working. There you go. So this is the web page for the Einstein Toolkit. Some information also about the upcoming workshops. So typically, every year there are 2 workshops for new users. One that is based in the US and one that is based in Europe, and they are coming up. So you can just go here to the download tab, and it has a bunch of instructions here. so this you just follow along these instructions to download to download the toolkit. Then the compiling is another aspect of it. So and this is and typically this part. I mean, it's not necessarily. It's not that it's very non-trivial. That's a bit time-consuming, and this is why I'm providing the virtual image that I was telling you before, because it's all of this is already done within the virtual image. So you just need to take that, and you're ready to use. Okay. So that's the point. But of course, in principle, it's totally fine if you just come here and you do it yourself in your own machine without the virtual image and without using VirtualBox, right? So VirtualBox is not needed to use the toolkit. I will just try to use it here during the hands-on session just for convenience. But you absolutely don't need to use it, and people don't typically use it for say for production. Okay. So let me, sorry, wrong page. There we go. So let me go a bit into some details of, in some organizational details of the code, so that when we get to the hands-on session, some of these things are already a bit more familiar. So within Cactus, or the Einstein toolkit, things are split into what is called arrangements. So arrangements are collections of thorns which fit a common purpose, or at least have something in common with that warrants them being organized into the same arrangement. In particular, one can have arrangements for initial data, for analysis, for evolution infrastructure, for different sorts of input-output, and so on and so forth. Now, the toolkit also provides you with some tools. The three big ones are these ones that are listed here. So the get components, SimFactor, and Formaline. Get components is nothing but a fancy Perl script that allows you to download the code. So this is, I suppose, also for historical reasons. So because the development of different parts of the code or of different modules, it's not centralized. So this has historically been handled by different groups throughout the world, and the code is hosted in different places. And so that the user, the first-time user, when it's just trying to get started with the code, doesn't have to be told about where to get which bit bucket to go and get this initial data, which GitHub to go and get this evolution routine. There is this get component script that basically just downloads the whole thing for you. That's what it does. SimFactory is a tool that is used for you to manage your simulations, and Formaline or Formalin is a tool that makes it so that allows you to store with your simulation data also the code that was used with it, so that then in the future, 5 years later, when you get an email from someone saying, "Oh, I saw your paper on the archive. I was wondering how you got this result," and then you have you have the data somewhere, you have no idea which version of the code you use to produce those results. Well, if you use Formaline, things are archived properly, right? So it makes it easier for you to understand exactly which version of the code you use to produce a particular batch of results. Okay, so these are the main core Cactus arrangements. So these are I'm just listing a few, but this, we have Cactus base, which are, so typically things that have the suffix base are very infrastructure thorns. So in particular, so the Cactus base are infrastructure thorns for boundary conditions, coordinates, input and output, symmetries, Cactus numerical, these are things intrinsically for, well, numerical methods in a way. So time integration, dissipation algorithms, symmetry boundary conditions, specifying spherical surfaces, interpolations, and so on. Utils are for several utils, like checking that you are having NAND somewhere in the simulation, so that you're not spending your precious computing allocation just crunching a bunch of NANDs. Termination triggers, reports, and so on. And the external libraries allows you to interface with other libraries like HDF5. So this is used for input and output, FFTW, GSL packages, and so on. Now, one of the important components, as I was saying in the beginning, is the mesh refinement library. So the mesh refinement library within Cactus or within the Einstein Toolkit is known as Carpet. So Carpet implements a Berger Oliger style adaptive mesh refinement driver. So the idea is roughly what is being shown here in this cartoon. Well, this is actually more a cartoon of a cartoon. This is an actual snapshot of a simulation. So, and this is a typical grid that you could use, for instance, for a system of binary black holes. So there you have one black hole here, another one black hole there, and so of course you need to properly resolve each of these regions around that are very close to each of the black holes. So you need many grid points here. But if you're further away, I mean, if you're around here, well, you don't need as many grid points, and in fact, you shouldn't have as many grid points, because you would, if you would, very quickly run out of memory, of RAM, in your machine. So you need to have a tool that sort of provides a way for you to be able to specify such a grid, and this is what Carpet does for you. So you have, so here we have two inner grids in the vicinity of each black hole. I mean, it could also be neutron star, so each compact object. Then you have a common grid, which is has slightly less resolution. Then you have yet another one here, which has even less resolution, and then you have one that has even less resolution here, and this is. And then you have this sort of spherical patch. So then you have this grid in that uses some sort of spherical or spheroidal coordinates that sort of patches its way here, right? And all of this is done by the Carpet library in a way that should, in principle, be seamless for you, right? As you are coding your new initial data Thorn, or your new analysis routine, or a brand new evolution scheme, you shouldn't need to think about any of these, okay? And then in the back end, Carpet is doing for you is setting up all the mesh refinement and the grid hierarchy. It's communicating ghost cells information between the MPI processes. So I didn't mention this before, but of course, for efficiency, the whole of the numerical grid is then split among all the CPUs that you have available in your system, and which then, of course, need to communicate the information between themselves. Again, this is not something that you should be worrying about. This is something that Carpet should be doing for you. And it also, I keep losing my mouse, and then it also performs the parallel input and output, okay, in an efficient way. Okay, so then we have an arrangement which is called Einstein base. Oh, and that I should mention, of course, you're free to use, in principle, Carpet. It's something that, again, you can use. I mean, it doesn't rely or care about Einstein's equations in any way, okay? So if you have any sort of time evolution problem where you need to resolve your grid in this particular way for I don't know, say for Maxwell's equations for fluids, you're fine using the infrastructure, okay? But then in particular, if you really are interested in Einstein's equations, then there are a bunch of arrangements, a bunch of thorns that the Einstein Toolkit provides in order to make your life easier. So in particular, we have the thorns ADM base. These are the ones that define your space-time variables. We have the thorn hydro base that defines your hydrodynamical variables. You have this T mu nu base, which defines the right-hand side of Einstein's equation, so the T mu nu. You can register. So if you're doing hydro simulations, you can register your favorite equations of state. There are a few that are provided, and etc. So the point of defining things or using this ADM base infrastructure is that it holds everything together, right? So this is the whole point of Cactus. It's modularity. Okay, this is a very big thing of this framework of this tool, and the underlying idea is that you should, in principle, be able to hot swap your evolution routine with some new evolution routine that you think that is way more efficient, that's way better, and just keep everything else the same. Okay, so you should be able to switch to change your evolution routine, and your analysis routines and your initial data routine shouldn't care at all. Okay. And in order for you to do this, you should be using this AVM base variables. So basically, this defines a group of basic variables for the metric, the extrinsic curvature, and the gauge. And then, as long as you're always using these groups of variables, you can, as I was saying, you can just change your initial data routine to something else, and you're not touching your analysis or your evolution routine, and things should seamlessly work. Okay. In the same fashion, we have the thorn that does exactly the same, but for the variables that you need for the stress energy tensor. These are the time component, the mixed components, and the spatial components. So those are the routines that are really only defining your fundamental variables that you should be using, and then you can use them in all the other thorns, in particular in the thorns that provide your initial data. So one of the most widely used ones is this two punctures, which allows you to write binary black hole initial data. So for vacuum configurations, this works fantastically. Okay, so you're able to specify whatever spin, whatever initial momentum, and then two punctures that solves the initial data equations for you and sets up your problem at your initial slice. There's also a TUV solver. So if you want to specify the initial data corresponding to a single TUV star, so Guilherme was talking about that. So there's a thorn that allows you to do that. And then there are assorted hydro-related initial data thorns. So for the metric evolution thorns, this is actually a bit outdated because now we have in the toolkit more thorns than just these two. So the classic one is for to evolve the space-time is McLachlan here. I keep losing. Yeah, McLachlan here, which is a BSSN and Z4 evolution code. This is machine generated, so it's not something that's very human readable. There's also the lean code, which again, it's a BSSN evolution code. This one is readable, and it's written in a very pedagogical way so that you can understand what's going on. So now there are even other alternatives. For analysis, so there are thorns that allow you to find the apparent horizons as you are doing your evolution. There are thorns that allow you to compute the Newman-Penrose scalar psi4, which is obviously very useful if you want to compute gravitational waves. There are tools that allow you to do this, the multiple decompositions of these quantities. There's a bunch of tools for you to compute quantities from the AWGAM variables. There is even a thorn that allows you to find the event horizon. So not just so here these two here are for the run as the apparent horizon one. So the apparent horizon is a local quantities is a local quantity. So these two here they run like on the fly, right? So they are finding the apparent horizon as you're doing your numerical evolution. But there's also a tool that allows you to look for the event horizon once your simulation is once the simulation is done. I'm not sure how much this one is up to date, though. I haven't used it. Okay, so now a couple of things about the tools that are provided. So the SimFactory is a tool that allows you to manage once you're doing many simulations and you're doing many runs, and then it's difficult for you to keep track of what's running where. So SimFactory is a good tool for you to do that management. It also provides a very helpful list of widely used supercomputer configurations, so that you don't need to spend your time trying to compile the code on those machines. So someone has done it for you, and it has provided that configuration file. So then you just need to say, okay, I'm running on this machine, and then the code just chooses the relevant configuration file and does the compilation. Now, we are approaching the part of the hands-on session. I will start. Well, first I'm flashing this again. So for those that would like to install VirtualBox. And then the exercise would be, so I will start though. So before we actually go into so I'll leave this here for just for a little bit. But in any case, the idea for the beginning. So before we actually, I'm not sure if I'll probably do that only tomorrow. But the idea for the beginning of the hands-on session would be for us to follow along an implementation from scratch of a cactus storm. Okay, so of course, I mean, it would be extremely difficult for me to guide you through a full implementation of Einstein's equations. So what I would like to show you for the next few slides, and then once we actually go into the code, I can show you exactly where each of these files are and how this works. But the idea is that the idea would be to understand how you would use this infrastructure, the calculus or the Einstein toolkit, to implement the wave equation. Okay, so the wave equation is something that's familiar to everyone. It's here. Okay, just that, and it actually, I mean, and it shares a lot of. I mean, it may not look like it, but it does in a way. I mean, it shares a lot of similarities with what we want to do with Einstein's equations, right? This is an equation that's second order, it's written explicitly in a time-dependent fashion. So we, in principle, if you understand how the very basics of how to implement this in the Einstein toolkit, then we have a good basis upon which we can build to move along to more complicated setups as in the Einstein equations. Okay. So the first thing is the following. Typically, we want to be using what is known as the method of lines technique to perform the time evolutions. Okay. So in order to do that, so the first thing that we need to do is to rewrite these equations here in first order in time form. So introducing these variables, we can rewrite this equation in this fashion, right? So what we have here is nothing but the wave equation, the boring wave equation here. Okay. So these first three equations, so 1, 2, and 3, these are the equations that will be evolved, and the final equation will play the role of the constraints. Okay, so this is much the same way as we wrote. So as I showed you yesterday, the system of Einstein's equations, right? Cleanly split into a set of evolution equations and into a set of constraints. Now, so we will get back to this, but this is just so that, I mean, just keep this in mind. So this is what we want to be. This is ideal. So this is what we want to be coding. This is what we want to be evolving. Okay. Now, how do we do with implementing this in an actual in an actual Einstein toolkit thorn? So this is the basic anatomy of any cactus thorn. Okay, so this is this particular thorn. So it's called the wave mole, and once you have the code, you can find it in this in this folder. So we'll go back to this, but for now I just want to give you the basic idea. So we have, so pay attention to these files that are the .ccl. So there's a bunch of files here that are the .ccl files, and then there's a bunch of files here in a source folder. Okay, this is very, very generic. Every thorn is written in this in this way. Okay, and now I'll just go one by one, just to give you an idea of what these are doing. So starting with this interface.ccl file. So the CCL stands for Cactus Configuration Language. Okay, so these files, these .ccl files, are written in the let me call it the cactus, a particular syntax. So let me call it the cactus language. And this should be scrollable. Yes, I think yes, this should be working. And the way to think of this, at least it's the way that helps me to think about it. Ah, there we go. Now it's scrolled. The way that helps me to think about it is that this is sort of the so for those of you that are familiar with computing in C, this is sort of the header file. Okay, this is where you define your variables. So in particular, so I'm going to ignore this this early part, this part here at the beginning. So, but in particular, what am I doing here? So I'm specifying my basic grid functions. Okay, so this is phi and phi, what I'm calling this phi t. So which is the scalar field and the time derivative. So again, remember, our goal here is to evolve the wave equation. So the wave equation is phi, and then because we need to reduce this to a first order in time format, then there's the phi t, which is the first derivative, or the velocity, if you want. Okay. So I'm also defining as grid functions the spatial derivatives. So here they are, phi x, y, and z. And then I need to specify the right-hand sides for each of these variables. Okay. So the right-hand sides are nothing but this here, right? I mean, literally the right-hand sides of the evolution equations. So in this particular case, they're extremely simple because the wave equation is simple. But of course, in general, we would have something that could be way more complicated. Now, then we have the schedule.ccl file. The schedule.ccl, the way to think of this is precisely what the name tells you. It's the scheduling. This is the file where you're scheduling where each of your routines should be running. Okay, so Cactus, or the Einstein Toolkit, if you want, specifies for you a set of time bins. There's a time bin for setting up the grid. There's a time bin for setting up the initial data. There's a time bin for doing your evolution steps. There's a time bin for analysis, and so on and so forth. And then in your own code, you need to tell Cactus where to run, where to call your routines. Okay. So, and this is where this is done in this schedule file. If you want a way to think of this, again, for those that are familiar with computing in C, so if you want, this is your main.c. Okay. So if you're computing in C, I mean, you're familiar, you know that you have your main.c function, which, I mean, if you're following good practices, is just calling functions that you have defined in other files. So it's more or less the same idea here. So for instance, here we have a routine that is called at startup. We have another routine that is called at base grid. We have another routine that is called at register. So we have another, then we have a routine that is called at this calc right-hand side. So this is precisely where we are calling the function that is defining the right-hand sides for our evolution equations. And so here, for instance, this is to compute the energy, boundary conditions, and so on. So again, this is the, so if you code a very fancy, very pretty routine and don't schedule it here, then the code will never call it, right? So this is the point of this file. And then finally, there is this param.ccl file. Again, this is one of these Cactus files, and this is the one where you specify the parameters that you need to that you need in your code. For this particular one, we actually only have parameters that are related with the implementation, the numerical implementation, and not so much about the physics, right? Because the equation that we're interested in doesn't have any parameters really. Just the wave equation with the velocity that is the speed of light. So I didn't specify that as a parameter. So there are no physical parameters here. Okay, and then we have all the files. So your actual coding then happens in this source folder. Now, I'm probably going to skip this one. I would just like to note this particular file here. So this wavemol.c, this is where you're doing your the implementation of your of the equation that you're actually evolving. Now, here the important part is this, basically. So it may not look very immediate, but this is the only thing, really, the only thing that this is doing is taking a bunch of derivatives. Okay, this is just doing second order finite differencing operations, and what you find here is nothing. So if there was a blackboard, I could have written it down so that it would be easier. But what's been done here is exactly this. Okay? Nothing more. Okay, so now since we're running out of time, I will probably just use the remaining 5 minutes to show you what you should do with a virtual machine image that I hope you've downloaded. So I'm going to need to put this down. I will shout. Okay, so again, go to the VirtualBox webpage. You follow the instructions to download whatever, for whatever system you're using. So if you're using Windows, these are instructions here. For Mac, for Linux, even though if you're using Linux, there's a fairly good chance that your distribution already has this in the repositories. For instance, mine does, right? So for me, the only thing I had to do was this with Fedora. With Ubuntu, I'm not sure, it's been a while since I've used Ubuntu, but I'm fairly certain that should also be provided with the Ubuntu repositories. But if not, it's you can find it for sure here in the VirtualBox webpage. Okay. Now, once you have it, then what you need to do is you fire it up. Wrong screen. No. Change my display here. It's not showing properly. Give me 1 second. Ok. Então, cá está. Sorry, wrong language. So, assuming that you have this installed, okay, you go here, File, Import Appliance, you pick the image file. So I already have it, so if I repeat it, it'll probably mess up the whole thing. But you pick the image file here, you choose it, and then you just click next, and the virtual box should import. It should just take a few seconds, and then you should have your image file accessible here. So it should, if everything goes well, it should show up here. Okay. Then here you can just fire it up. Okay. There we go. So I think we're out of time for this session, but please give it a try at home, okay? And then tomorrow we will resume from here, okay?
Thank you, Miguel. Any questions?
Thank you, Miguel. Do we have to write the metric and curvature extrinsic tensor in Cartesian coordinates, or can we write it in spherical coordinates, cylindrical coordinates? Because in your slides, basically you show it in Cartesian coordinates. So.
Right. So intrinsically, so it's a bit non-trivial. So it's Cartesian coordinates. Okay. So the main thorn that specifies your grid works or expects Cartesian coordinates. Now there is another thorn that is called multipatch that allows you to do a coordinate transformation to a grid that is spherical-like. Okay. But in principle, the underlying, the more basic thorn, the one that specifies your full grid, this expects Cartesian coordinates or Cartesian-like coordinates.
Any more questions? No? So let's thank the speaker again.